This last unit, or excuse me, this last lesson of our unit, we're now going to look at how we can look at the angular/rotational analog of linear momentum. Angular momentum and impulse, the topic for 7.5. So angular momentum and rotational analog of the momentum impulse theorem. So the angular momentum, which we represent by the letter L, describes an object's strength of rotational motion, just the same way as linear momentum describes an object's strength of linear or translational motion. Angular momentum depends on the moment of inertia I and angular velocity omega, just the same way as linear momentum depends on the mass of an object and that object's linear velocity. The units we have for angular momentum are kilograms times meters squared per second, which comes from if you do some unit analysis with the equation for angular momentum, which the equation for angular momentum is angular momentum equals moment of inertia times our angular velocity. So again, it's a carbon copy and rotation. It's a carbon copy rotational form of linear momentum, except we replace mass with the rotational form of mass, moment of inertia, and we replace linear velocity with the rotational form of linear velocity, angular velocity. So similarly, just as we require an external force in order to change an object's linear momentum, in rotational motion we require an external torque acting over time to change an object's angular momentum. So we have the momentum impulse theorem for angular momentum. It states that our change in angular momentum, which is given by the moment of inertia times the change in angular velocity, is going to be caused by, hence the equal sign, a net torque acting over time, represented by torque times time. So again, we can see that this is exactly like the linear momentum case where we had the change in linear momentum, mass times change in velocity, equals the force is caused by a force acting over time, except now we have force replaced with its rotational analog of torque, and we have linear momentum replaced with the change linear momentum replaced with the rotational analog change in angular momentum. So the principles for the angular version are the same, all right, as we've seen. So everything that we've seen that's been happening for translational variables is also happening for the angular version of those variables. So if we want to graphically interpret angular momentum versus time graphs and torque versus time graphs, we apply the same principles as we applied for linear momentum versus time graphs and force versus time graphs. So the same way that the net force acting on an object can be calculated as the slope of the linear momentum versus time graph, we can also calculate the net torque acting on an object by calculating the slope of the linear momentum, or excuse me, the slope of the angular momentum versus time graph. So net torque is equal to the slope of an angular momentum versus time graph, which gives us our change in momentum over time. Okay, and again, we get that the same way that we saw with the momentum impulse theorem, where we divide both sides by t to get torque equals change in angular momentum divided by time, or the slope of an angular momentum versus time graph. And then also we can calculate change in angular momentum from a torque versus time graph. So same way that the area beneath a force versus time graph gave us our change in linear momentum, the area beneath a torque versus time graph will give us our change in angular momentum. The idea being, again, is that torque versus time is like height times width, or base times width gives us the area of a rectangle, and torque times time is also equal to, by the angular momentum impulse theorem, our change in angular momentum. So the area beneath a torque versus time graph is going to give us the change in angular momentum, just as the area beneath a force versus time graph will give us our change in linear momentum. So it's nice how all the principles that we see from translational motion also are held up for rotational motion as well. And again, here's a nice visual of what we've been talking about, just like we saw back in 4.1 when we first started studying linear momentum and the momentum impulse theorem. So now we come to center of mass, which is something we've talked about before conceptually, but now we're going to delve a little bit deeper and dig into the mathematics of it. So if you recall, we have talked about it before. The center of mass is the point that's representative of where all mass in a system is concentrated. For systems with no hinges or fulcrums, this is significant as it represents the axis of rotation for the system. So if we don't have our system connected, if an object connected to a hinge or a fulcrum, that object is going to rotate about its axis of rotation, which is going to be the center of mass. So to calculate the center of mass, we calculate what's called a weighted average, where each point of mass, what we call mi, is assigned a relative weight to the other masses based on the position of that mass, okay? So when we say weight right here, we don't mean like the force due to gravity. We mean, it's a mathematical term that means we give more importance to some masses relative to other masses depending on the position of that mass. So the position of the mass will determine how much importance that mass has. So the weight here just means the amount of importance each mass has, okay? So as a result, right here, if we have a system of masses right here, okay, M1, M2, M3, and M4, the center of mass is going to be calculated by taking M1 times X1 and adding to that M2 times X2 and adding to that M3 times X3 and adding to that M4 times X4. So we're going to take the mass times its position, and for each mass times its position, we're going to add up all those mass times positions, which is represented by the top term right here, sigma mi xi. And then what we're going to do is divide by the mass, total mass of our system M. So this is why we call it a weighted average, why we call the center of mass a weighted average, is because this is actually the average equation right here, sum of all our masses divided by the total mass, which would typically give us our average mass. However, by multiplying by the position xi, we're assigning to each point of mass a relative amount of importance. So depending on where the mass is located, it will either have more importance or less importance to our overall system, which helps us to determine where the center of mass is. If this is still a novel concept to you, don't be turned off by it. Just kind of take it at face value right now. This is a statistics concept that may be countered, say, in AP statistics or college intros to statistics course. But for here, we just need to take it at face value. So the X right here gives a relative weight or importance to each individual piece of mass, okay? And this equation does have to be memorized as it's not on the equation sheet for AP Physics 1. So let's take a look at an example here. Let's calculate the center of mass on a seesaw. So a 10 kilogram mass is situated at the left end of a 2 meter long seesaw, while a 2 kilogram mass is situated at the rightmost end. What is the center of mass of the system? Let's assume we can neglect for a time being the center of mass of, or the actual mass of the seesaw, and we're just concerned with the 10 kilogram and 2 kilogram masses. So here's what our scenario looks like. We have a 10 kilogram mass at the leftmost end, and we have a 2 kilogram mass at the rightmost end. So what we can do here is we can choose to determine where we want to measure our center of mass from. So we can choose to make this 0 meters right here, and then our 10 kilogram mass would be at -2 meters. Or we can choose to make the 10 kilogram mass located at 0 meters and thus a 2 kilogram mass at 2 meters. In physics, it's a standard convention to always measure from the left going right, just as we do in everyday life. So in this case right here, we're going to assign the 10 kilogram mass a position of 0 meters, and then we're going to assign a 2 kilogram mass a position of 2 meters. So M1 is 10 kilograms, X1 is 0 meters, M2 is 2 kilograms, and X2 is 2 meters. So as a result, our equation is going to be for our center of mass, sum of each individual mass times their relative position. So we're going to have 10 kilograms times 0 meters, M1 times X1, plus 2 kilograms times 2 meters, M2 times X2, divided by the total mass of our system, which is going to be 10 plus 2 kilograms, or 12 kilograms. So as a result, we're going to get that our center mass is 0.3 meters. So our center mass is not going to be located at the center of our seesaw, but it's actually going to be located closer to the 10 kilogram point. So this result makes sense as more mass is concentrated at the left end, so our center of mass should be closer to the left end. So that's so even without knowing statistics or making sense of the mathematics of what a weighted average represents in terms of statistics and math, we can make sense of it from the physics perspective in that the weighted average gives us what we should expect to happen, namely that the center of mass should be located more towards the end of our seesaw that contains some more mass, which is what the weighted average gives us right here. So we can see the center of mass and the weighted average match up very nicely with what we'd expect to happen in reality. So next we come to conservation of angular momentum. So just as linear momentum is conserved for a system, so too is angular momentum conserved for a system where no net external torques are acting. All right. So so again, the big caveat is no net external torques are acting on a system. Okay. So that means we can have forces. We can have external forces acting on a system so long as those forces do not cause torques. Just as we've seen before, there are cases where forces can act on a system but not cause a torque. So a net force is fine so long as that net force does not cause a net torque. So angular momentum is conserved if no external torques are acting on a system. And we'll explore this in more detail when we get into class tomorrow with some discussions and some potential scenarios to help us critically think about what's going on here with angular momentum conservation and how it might be related to or different from linear momentum conservation. So conservation of angular momentum tells us our initial angular momentum is equal to our final angular momentum, or that our initial moment of inertia times our initial angular velocity is equal to our final moment of inertia times our final angular velocity. So just as we've done before, the problem-solving process is the same as we saw in Unit 4 with angular momentum problems or with linear momentum problems. We write down what we know before and after our collision. We set the initial angular momentum equal to the final angular momentum. And just as we did with conservation of energy problems that involve rotational energy, rotational kinetic energy, we're going to convert to linear variables or angular variables depending on what the problem asks for. And then lastly, we're going to solve for our unknown quantity. So let's take a look at what this looks like in practice. Oh, and actually one real thing that we can use, a nice little cheat code, this isn't on your equation sheet real quick. This isn't on your equation sheet, but this is a very useful result to memorize, is that if you're working with a point mass, okay, the angular momentum of that point mass in terms of linear variables is going to be mv times r. The idea being is we start off with the equation for angular momentum, moment of inertia times angular velocity, and we replace moment of inertia with the moment of inertia of a point particle, which is mr squared, and then we replace omega with, we replace our angular velocity omega with v divided by r, our linear velocity divided by the radius of our object. And so as a result, that gives us mv times r as the angular momentum of our object in terms of linear variables. Okay, so let's see what this looks like in practice. So a rod of length L and mass 3m that rotates about its center, like we see right here, okay, is hit by a ball, I'm mixing together all sorts of words here, is hit by a ball of mass m moving at speed v. The ball and the rod stick together after the collision, rotating with an angular velocity omega. Determine omega in terms of m, l, and v. So this is a typical problem that you might see on the AP Physics FRQ section or in the multiple choice section, although it tends to be more common on the FRQ section. The moment of inertia of a rod about its center is I equals 1/12 ml squared. Again, don't worry about how we get that equation. It comes from applying calculus to moment of inertia for random geometries, arbitrary geometries. So we start with what we know before and what we know after, okay? So before, we know that the angular velocity of our rod is 0. It's just sitting there at rest, okay? We know that the angular velocity of our ball, okay, in terms of v and l is going to be equal to negative v divided by l over 2, okay? The l over 2 comes from the fact that our rod is a length l, so that means our ball is striking at a distance L over 2 from our axis of rotation, since the axis of rotation is at the center, okay? And then you may be asking, where's the negative sign come in? Well, this negative means right here that we're going to be moving in the in the clockwise direction, which is what's going to happen to our ball. If we see this scenario happening and playing out to the right here and playing in our heads, when the ball strikes the rod is going to start rotating in the clockwise direction, telling us our ball is moving in terms of an angular velocity in the clockwise direction. So we have a negative sign right here to account for that negative, or for that clockwise direction. So as a result, the initial angular velocity of our ball is going to be negative 2v divided by L. All right, so that's what we know before for our system. Afterwards for our system, okay? Afterwards for our system, our ball and the rod stick together, so we're going to have one final angular velocity. So that's going to leave us with one final angular velocity as our unknown, okay? And then right here, I do paint a picture to illustrate the L over 2 for the distance, and then to illustrate why the velocity right here of our ball would be considered clockwise. All right. So now let's move on to the next step here, step 2, all right? So step 2, we set the initial angular velocity equal to the final angular velocity. So initial angular velocity is going to consist of the initial angular velocity of the ball plus the initial angular velocity of our rod. Again, the rod is at rest, so the initial angular velocity of our rod is 0. So that's going to leave us with the initial angular velocity of the ball equals the the final angular velocity of the total system after the ball and rod stick together. So as a result, we're going to have the moment of inertia of the ball times the angular velocity, initial angular velocity of the ball, equals the negative moment of inertia of the ball plus the moment of inertia of the rod times the final angular velocity. So we have to add the two moment inertias together just as we would add masses together. And then you may ask, why is it negative right here? Well, again, our system after the collision is going to be rotating in clockwise direction, so our angular momentum is going to be negative. The final total angular momentum is going to be negative right here. Hence, we have a negative sign right here. All right, so this is where we're at. This is where we left off at. So now what we're going to do, since we're deriving omega f in terms of v, we convert to linear variables. All right, so again, here's where we make note of the fact that our ball can be treated like a point-like system. So we can replace the angular velocity of the ball with the equation that we looked at in terms of linear variables. So mv times r, which in this case, that's going to give us negative mv times L over 2. Again, r, our distance from the axis of rotation, is L over 2. So we have negative mv over L over 2. Okay? So now on the right-hand side, okay, what we're going to have right here is we're going to have negative ml squared times omega f. And I believe I actually made a mistake right here. This is supposed to be a different moment of inertia from what we have right here. So don't do what I just did right here. I just made a mistake. But anyway, we can see right here, we're going to sum our moment of inertias together, which let's assume I didn't make this mistake. And let's just assume for a time being that ml squared over 2 is correct. Okay. So forgetting the mistake I made and assuming that this is correct right here, we would next solve for our omega f by dividing both sides by m. And by negative signs, so negative signs will cancel out, m's will cancel out, and then the 2's will cancel out, which is going to leave us with VL equals L squared times omega f. Again, you should get a different answer here because I made a mistake where I forgot to plug in the moment of inertia of the rod, which again is 1/12 ml squared. But from here on out, the process is still the same even with this mistake I made. So dividing both sides by L squared would give us that our final velocity is V divided by L. And hence, this is a typical conservation of angular momentum problem. Again, the big hints that we need to make is converting to linear variables, which requires us to use, for any point-like system, the equation for the point-like angular momentum of a point-like object. All right. So again, these problems are easier said than done. This again is just to expose you to initial problem, and then in class we'll get more exposure with more practice problems and discuss how to do them together and get more practice together. And this is 7.5, conservation of angular momentum.